Okay, maybe like this will work better. Welcome again to our channel. I actually don't have anything planned for today, and this is kind of the problem. I maybe let me get Tobias. There you go. Um, I don't know what to do with the life, to be frank. I hoped that by doing some, we would find a sort of productive way to do things. I always feel that I'm completely unprepared and we just futz around. So I don't know, Tobias, what you think? Like, what would be a good way to use this time?
Wait, so I'm actually okay, I'm unmuted. So maybe we could or you could show me a bit more of what we already talked about yesterday. Like the whole business about Choquet theory is completely new to me. I don't know what you can teach me about this like right now without preparation, but that would be at least immediately helpful to me.
Okay, so we could go with a topic. So, Choquet theory in particular is something that I haven't quite fully understood. So there are some there are some moves that I see that are done over. So I could I don't know if I can teach something like Choquet theory or some other thing without preparing completely. But what I can do is, in this time, give insights that I've been accumulated either in the week, you know, in each week, or even things beforehand. So in a way that maybe some of those things can turn into videos because even there, like taking insights and making like actual videos with slides so that it costs more. So would that be something that would make sense?
So I think you were cut off for like 2 seconds, and now the sentence doesn't make sense. You can make small videos. Uh,
So
yeah,
uh, so one of the things that happens, right? Every week I'm working on things and I figure out something or I figure out the right way to look at something. And so I could on Saturday say, well, these are the things that I figured out. Because the other problem of the way that we're doing things right now is that not having a plan and not having a topic means I can't even prepare some kind of title or something for the live.
yeah,
So it's completely random what what happens, and people uh, you know, uh, can't prepare ahead of time to say, okay, this is going to be interesting to me, this is not going to be interesting to me,
yeah,
and so on. And so that's one of the problems. So when we had guests, at least it was clear there's a guest. This is going to be the topic, and then people can decide. And I can even advertise it in advance.
yeah.
I tried a couple of times to do sort of Q&A type of things, but I don't think we have a big enough viewership to do that. And most of the people that kind of do follow and so on, they don't engage in the chat either. So we don't know exactly what they would like to see either. And so that's kind of another problem, which I have no idea how to address. And
For Q&A, maybe if you explicitly encourage this, we could make like a list beforehand, and then like I don't know, we make one session and we collect enough questions until we can address them. Because if we then know, okay, today we are going to address these and these questions, then the people that ask them hopefully show up, and then this could that's good work.
okay, so that could be something because I do get questions under the videos.
Mm.
Right. So we could also take those questions and answer them here, which is a lot better than trying to answer them in a
Yeah.
paragraph inside. So that could also be something
Yeah.
that could be done. Um, okay.
Just a second. Okay, I'm just pulling up the chat as well, but just to see what's happening.
Ah,
Okay.
there is we also have Gabriel join today. Is Gabriel your, how do you pronounce it? Gabriel or?
Hello, Gabriel's fine. Either way is fine.
Okay.
Let's see.
So yeah, because so the issue is having some type of plan that I can always rely because I can't, people who do this for real, they stay there probably and think long and hard what to do, and they have probably even other people that help them to figure out, and I don't, I barely have the time to just do it. So, okay, so the plan of just saying, collecting questions from, yeah, I don't know. Like I already, I even tried at some point, what was it, a year ago, to basically make a video specifically on the channel that said, please list some question below, and then I'll make another video that responds to them. And I didn't get a single one. So I just
Uh,
don't, I just don't think we have critical mass for that. Also,
yeah.
maybe it's like the stuff that we do is not topical enough. Like if we had if all I did was videos on I don't know, interpretations of quantum mechanics, whatever, right? Then people would say, oh yeah, this is where I go and ask these type of questions. But this is not what we do. So
Yeah, that's true. Honestly, like what would happen right now would be very specific to our project. I'm not sure
yeah,
what other people could take away from that.
yeah.
That's kind of fair.
Otherwise, we just we just plan it to be the stuff for us where we do the research, or we do topics that are useful for me and you. Like when you're gonna have stuff, and when we're starting to going to work more on stuff, and you have things to report and so on, you can report them
Yeah.
also here. And probably and so basically becomes just a public group meeting for the stuff that we are doing, and that's basically it. And then that could be a solution.
Yeah. If you
Okay,
don't have anything else, I don't mind. Yeah.
yeah. So it might be that. So one of the things that could happen is that if we like from time to time, some people engage, like they write to me from around the world from our university and say, oh, how I can get more engaged. I wanted to do something and so on. And then the problem that they often disappear. And if there were like you basically, if there is the group meeting, say, oh, you can come to the group meeting, and we talk here, and then we can figure it out here. That may be a sort of let's say a normal way to do things in research anyway.
Yeah.
So yeah.
Okay, so for today, um, what I could use, and maybe since it's all spontaneous anyway, maybe we
Mhm.
stick to the big picture. Um,
Yeah.
so you in the last weeks you introduced like what you already have for like ensemble spaces.
Mhm.
Um, and at some point, I guess we have to connect, like make the actual connection to, I guess, probability theory, right?
Right.
So, and I guess this is where you have to put a measure somehow on like even on what like on a sample space like so the connection to probability theory is where the whole Choquet theory business comes in, right?
Yes. Because
So
that's it's a way to represent things with measures, with probability measures. Yes.
yeah, so since this is basically what we want to work on, um, I'm not so I'm not sure exactly what we want to do. Like,
Okay, let's do that. Let me
yeah,
get my tablet going so that Let's see. Let's see if this joins.
Actually, I will take a minute just to go to the toilet and then I'm
Yeah.
back.
And then, oh, I had this problem. There you go. And now I can, there should be a share button somewhere. Oh, I need to, there you go. That's what it needs to happen. And then we share the screen and we get this. And then we get, didn't I? Why don't I make a folder, call it live, and then there we go. Okay, so I'm ready. Tobias, are you back? Probably not. Okay, so let's do this. Let's start writing some things. So we want a probability space. A probability space is a sample space, a sigma algebra, and a probability measure. There we
Okay,
go.
I'm back.
Okay. So, big picture, big picture, big picture.
Okay,
Let's
this part I
do
understand. I just need to know how it connects to ensembles.
two ensembles.
They-
Okay, so if we start in classical mechanics, right, we know that the construction that we have. So this is a probability space, right? A probability is a sample space, a sigma algebra on the sample space, which you can think as all the statements that are linked to experimental verification. So for each statement, there is an experimental test. It might terminate, it might not terminate, but there exists one. And then you have a probability that assigns for each element of the sample space a number from 0 to 1. There we go.
Okay, and in the sigma algebra, they are not just the experimentally verifiable ones, but
They
even
are
the
the theoretical
theoretical
statements.
statements. Yeah. So
So
the negation must be at least verifiable.
it's not verifiable. You have the negation, but there is no requirement on verifiability. So you have a statement and you have the test. The statement can be true or false, and the test can terminate successfully, terminate unsuccessfully, or no termination, not terminate. Okay?
So we would even have statements where the test would never terminate,
Yes,
but at least we have a test.
but you at least you have a test.
Okay.
Okay, so that's how it works. And this is how, let's say, standard classical probability works. Okay, so in our contest, we want to say something like basically also Ariel says the probability is always this. There's nothing else. There is no quantum probability. There's just probability. And all the probability works like this.
Yeah.
What is different for us in quantum mechanics is that the space of ensemble is not does not is not the same. Is not equal to a probability space. because there are essentially two things that we might call probability, but they're different. One, if I have my ensemble here, right? Then I make an experiment and I can think of branching this into a different possible final measurements, final values. This is what we call probability. So the probability is the thing that you take out. It's I have a bag of stuff that I don't know. I reach out with my hand, I pick something. What is the probability that I pick something? Right? So I'm taking something out, and then I assign a number that tells me how many times I'm taking this out conceptually. What's the propensity of getting a particular thing out with respect to others?
Okay.
Okay?
Yeah, that makes sense.
And the difference between the sample space and the sigma algebra is that what you get out are never the points of the sample space. There are always statements of the single algebra. So if I have a number from 0 to 1, I never pick, square root of 2 over 2. I don't pick that. I don't pick a half. I don't pick a quarter precisely. I pick an interval. Right? I'm going to pick that the number that I get is between 1/2 and 1/2 plus 1/6. Okay? So the probability is assigned to those statements. It's not assigned to the points.
So the sigma, no, the omega, the sample space.
Yeah.
We basically think of it as all the limit points of the sigma algebra in some sense.
That's how I used to think it. I don't know whether we can actually do it like that. So the whole problem that I have right now is figuring out how we get the sample space. So
Okay, but conceptually still we start from the sigma algebra because they are connected to the actual statements, and then somehow we go backwards. Right?
Exactly. Yeah.
Normally you would naively maybe think the other way around. Okay.
Right. So the way that we get the sample space when we're doing where we're not doing ensembles, we start with a set of verifiable statements that is countably generated. So we have a countable base of verifiable statements, and we can generate all the other verifiable statements by finite conjunction and countable disjunction.
Yeah.
Once we have that, then we say, okay, we add the negation as well. And then we find the points. Because what happened is that our sigma algebra is countably generated. That is, there are countably many statements that can reach through negation, countable conjunction, and countable disjunction, all the other statements. And so what happens is that the sigma algebra is a lattice, meaning that you have, if I have two elements, you can do the join, which is going to be the end. You can do the or, so this would be the or. You can do the meet, you can do the end, and so on. And because everything is generated by a countable sequence, if this is let's say the impossibility, the zero, the thing that never happens, all you're going to have what they're called the atoms, and the atoms are going to be things that are sort of broader than the impossibility, and there is nothing else in between. Right? It's like the smallest statement that you can have before becoming something that can never happen. Right? And these become
So it is
essentially.
not the and or of something else.
Say again?
It's not the and of something else, or it's not the or of something else.
It's not the or of something else.
Okay.
Right? With the or you go up, and with the and you go down.
Okay.
Okay? And what happens is that these all these elements are basically your sample space.
Uh-huh.
And this happens because our sigma algebra, we're guaranteed by experimental verifiability that our sigma algebra is countably generated because we can only test up to countably many statements. After that, we can't create a procedure that explores all of that. And since the sigma algebra is closed up to countable operations, the smallest points that you can get are going to be the countable end of each element of each element of the basis taken as it is or negated. Right. So if your basis, let's say, is made of elements that are bi, right, from I equals 1 to infinity, then each element here is going to be something like B1 and not B2 and B3 and B4 and so on. So you take each element taken once, either not negated or negated. And those are the points.
This is okay. So each of them is just a sequence of zeros and ones.
Each element is just a sequence of zeros and ones, yes.
Would they themselves also form a basis that I can use?
No.
Right. Okay.
This is the thing that it seems counterintuitive, but the basis is not made by the points. If I give you the points, you are not going to be able to reconstruct the sigma algebra. It's like the same saying. So if I had arbitrary union, right? And I had these points, right, all the points, then any arbitrary set of points would become a set, right? It would become an element of the sigma algebra. And so your sigma algebra would effectively be the power set, right? And
So because those would be like the elements of my sample space.
Yeah.
If I am allowed to take any union.
If you can take any union, then any set of your possibilities or your points or your atoms is an element of the sigma algebra.
Yeah, because I basically included all the singletons from the start.
Right. So these are the
Yeah.
singletons, right? These
Yeah.
The points here are technically the singletons. They're not really the points. They're the singletons of the points.
Yeah.
Right. And the fact that we do not have arbitrary union in the sigma algebra is important because it's not true that any collection of points is going to be something that is associated with a test.
Yeah.
Okay. And so really the thing that generates the space are essentially the verifiable statements, the open sets. Those are the things that connect to experimental verification. And the points are just limits of those things. And you can't think of the actual statement as being constructed only from the points. Like it's the other way around. If you were to construct from the points, somebody would need to tell you which set of points are valid and which set of points are not valid.
Yeah, that makes sense. Yeah.
Okay. And so again, to make it more concrete, your sample space could be the real line, and a basis for the topology would be open intervals. And actually, you even have open intervals on the rationals, right? So if you have open interval on the between two rationals, that's a countable basis because the rationals are countable. If you take two rational pairs of rationals are also countable, and now you have a countable set of open sets, and from that you can recover all the other points. So this reverse process that we have as part of physical mathematics, where we start with essentially open sets and then recover the points, that's the stuff that we already have.
Okay. So also, if
Wait, I have a question from the chat.
Yeah.
Why is the countably infinite conjunction of verifiable statements verifiable? Okay, So it works like this. If I have a verifiable statement, the my diagrams look like this, right? I have true, false, success, undefined, and failure, right? This is how it works. Now, suppose that I have a countable sequence of my verifiable statement. I have V1, V2, Vn, and then so on, right? If I wanted to verify the conjunction, if I wanted to verify the end, I would need to test all of them and wait for all of them to stop and tell me that they're successful, right? And since I have countably many, I might take an infinite amount of time, and therefore I'm not be able to guarantee that I can verify the end of all of these things in finite time. Now, if I am verifying the OR instead, I can test finitely many, right? And if one is true, I can quit the process and say, yeah, I am successful. So if I have a countable connection of a verifiable statement, I can sort of go through the list, test the first one for an hour, to start testing the first one, wait for an hour. And that doesn't work. I start testing the first one for for 2 hours, the second one for 2 hours. It doesn't work. I test the first for 3 hours, the second for 3 hours, the third for 3 hours. Aha. The third actually terminates after 2 hours and a half. That's true. Then it means that the disjunction is true. So the conjunction is not is only finite conjunction that it's verifiable because you have to wait for all the tests to finish. But the disjunction, the or, as long as you have one, you can stop and you're done. So it's clear then that all the points here, right, since they are a conjunction of my bases, they're not necessarily verifiable. And in fact, on the real line, if we take a point, right, and we say the mass of the electron is exactly zero, right? That's the typical mass of the photon is exactly zero. That's the thing that I always have. That is not verifiable because it will require infinite precision, and we can't test with infinite precision in finite time. That make sense, Bedbot? Hopefully.
And the chat might have a bit of delay.
Yeah, there is. Okay, so assuming that we go on, otherwise we can always go back to this. Okay, so
Actually, I have a quick question, which is if my basis is countable.
yeah,
Oh, he just replied, by the way.
say it again.
He just replied in the chat.
Okay. It's a locale with only countable join and the usual path. So quite frankly, there are three different things in sort of category theoretic kind of things. There is the locale, there is the frame, and there is something else. And I never quite understood the difference between them. I talked also to some people that know more than me, and they told me that it's a difference on the morphism more than on the space itself. And I, quite frankly, we weren't able to figure out exactly what was what was the difference and which one I need exactly, which is the correct morphism in the categoric theoretic way. So I still think as these as essentially topological spaces, because the morphing that I have are going to be the continuous functions. If there is somebody that can help me figure out exactly what's the correct language in categoric theoretic way, I'd be delighted, and we could have a discussion here on the live to figure that out, because it would help me understand, how other people think. But again, I was not able, so I can't confirm that it's a locale because I think it's a locale, but I don't know if the morphemes defined in locales are exactly the thing that I have. I don't know if that makes sense.
But that would actually be a cool thing to do here. Like if we would find someone who could actually explain this to us,
Yes.
that would be so useful. We could like even advertise it as like, I don't know, category theory for dummies.
Yes. Well, the problem again, category theory. I mean, I'm getting more and more. I'm starting to understand more and more even the history of the transition of some things, and there is this like more and more algebraic slant on things that I don't know if it's the right thing that we want for physics. Like even the whole notion that we were talking even last week of vectors as derivation and so on, right? That's sort of a way to talk about vectors, to study vector and differential geometry in a more algebraic way than the standard way that people used to do, I guess before the 60s or whatever, the current way started to become popular. And but the objects that we're trying to study, I like, yes, they're going to be isomorphic to some algebraic structure, but I don't think they are themselves algebraic. So it's one of those things where the mental model that you have in physics doesn't quite map the structure that you have in math, and then you always have to make these translations, and they become cumbersome. So. But yes, hiding algebra is the other one. Do you know this stuff more in details? Like, would it make sense for you to join the Zoom call, or you are also another like? Okay, there is a lot of delay here. Anyway, if you know this stuff more than Aspetbot and you'd be willing, but we probably need to review your work. Okay. Uh, let's see. How do we want to do it? Um, should we try for next week so that we have something to talk about next week? Do you want to reach out to me during the week so that I can give you the links, and maybe we can talk a little bit beforehand and prepare a little bit? Would that make sense? Very good. Okay, so we can do more fun. This is kind of what I like to have exactly. This is the prototype of the ideal thing. We discuss something. There is something that knows more in the chat, and then we bring him in and we have a better discussion about it. So, okay, good. Okay, so let's postpone that discussion then, and let's go back to this to your question, Tobias. What were you
Yeah,
asking?
just for intuition, if I
Yeah.
have a countable basis, like an actual countably infinite basis, like
Mhm.
the natural numbers, if I then look at this sample space as a sequence of zeros and ones,
Yeah.
I guess I can interpret them as like real numbers, right?
Yeah.
Just digit expansion of this. So the sample space
Yeah.
will always have the cardinality of the real numbers
Yes, or less.
or less. Okay, but then only if the basis already is smaller.
Uh, Not necessarily. So what happens, what can happen is that some of these elements of the statement may be incompatible with each other. So, you have B1 and B2, and there are two separate statements, but they can never be true at the same time.
Okay, so some sequences would be excluded.
Exactly.
Okay, okay.
Because they become impossible, right? So if you do the A and B, you get you get the impossibility, you get the zero already.
Okay.
So you can think, for
Which
example, as the natural numbers as having the base. Is it one? Is it two? Is it three? Is it four? Right now you have a countable bases because the statements are countably infinite, but they're all independent from not independent. They're all incompatible with each other. So if one is true, all the other ones are false.
Okay. By the way, which structure here tells me what's compatible, what's incompatible?
Uh, it's basically the lattice itself. Like,
Okay, okay, good.
yeah. Okay, so this is our probability space. We have essentially our sigma algebra, which is basically a Boolean algebra. We have elements of this Boolean algebra we assign 0 to 1, and we can think of as elements of the Boolean algebra as made of essentially as being collection of points. And this is the classical probability, as I was saying. It's the thing that we take out. So we have an ensemble, we prepare the ensemble. Then we have an experiment, right, that sort of extract information, extract something out of that ensemble. And we have different cases, and these different cases are going to be elements of the sigma algebra, not the points. And so it's a probability of what happens essentially at the end, like you're taking things out, right? And the issue is that not everything is like that. So we say this is the ensemble. This is the probability that we get out. What we can also have is that we have a bunch of ensembles that are coming in, and we mix them. And it's not necessarily the case that these mixture coefficients are the same as probability coefficient.
So classically, if I mix the ensembles, then also the probabilities would be mixed. Like I make
Yeah.
the same convex combination, right?
Correct.
Yeah.
So this is the thing that is different from classical mechanics and quantum mechanics and probably other theories. That if we need a different theory for Planck scale that is not going to be quantum mechanics, it will still have this property. The fact that mixtures are not necessarily probability of outcomes. Right? So mixtures are mixture of ensemble when we're putting things in. Probability of outcomes, we're taking things out.
Yeah. Okay.
And the probability is always additive because if we have two outcomes, either one happens or the other happens. And so if we have a probability for this and a probability for this, and now we put them together and we say, we take the elements of the sigma algebra that says either we have this or we have this, the probability is going to sum.
Yeah.
Okay? With mixtures, you can mix things that you're not going to be able to distinguish with one set of probability with one measurement. So again, we have the block sphere. If we mix spin up and spin down, then the mixture is also the probability. But if we mixture spin up and spin left, what we get is going to be the point in between these two. For example, if we mix 50% and 50%, and we do not have a measurement, we don't have a process, right, that can make these two things to mutually exclusive outcomes. The only outcomes that you can have multiple exclusive is things that are on an axis. And therefore, the probability that you get out, for example, if you measure up and down, right? Since you're measuring this, what's going to happen is that you're going to have a higher chance of getting spin up than you had when you mixed, because it's going to be the probability that you actually put spin up plus essentially 50% of the probability that you've put spin right. Because if I start with spin right, I have 50% of probability of getting up and 50% of probability of getting down. Okay, so this is the thing that is confusing in quantum mechanics, but once you realize that there is no, can I say, there is no need for when you mix things, you get out the same probability. Like if this, even if you even work with classical distribution, this would also not be the case. So once you realize this, that's fine. Like all of quantum mechanics becomes, oh yeah, of course, there is that.
Okay. The probabilities that you assign, like the boxes that you draw on the right, are
Mhm.
they ensembles? Are they elements of my sigma algebra, of my sample space, or whatever?
Good question. So these are the things that are still open in my mind, and I'm trying to figure out what these things are
Okay.
and what's the correct way to think about it, and how are we going to get these things, formulated precisely so that then we have mathematical axioms definition that when a mathematicians look at it, it says, oh yeah, this actually makes sense. In principle, one of the things that I think is a problem is thinking at I can say, I do think that these are going to be ensembles themselves, but they're ensembles of the output of a measuring device.
Okay.
And it's the measuring device that has the requirement that the outputs have to be mutually exclusive.
So they are somewhat special ensembles. This is basically where, I don't know, if you think quantum mechanically, where the collapse happens, you now have something like definite outcomes. Is that what
Yeah,
you need?
yeah.
Okay.
So if think it like this. Again, we have the block ball, right? And we have somebody that prepares an element of the block ball. They could prepare this point, they could prepare this point, they could be preparing any point. And again, the point is an ensemble, which means somebody is not just preparing something once, but it has created a preparation procedure that can be repeatedly used to get elements of those ensembles. Okay, so each of the points here is an ensemble and represents a preparation device. Now, you want to, let's say, construct a measurement that measures the spin up or spin down, right? Then you say, okay, these 2 points, right, are distinguishable from each other. And how do I know from the ensemble space that they're distinguishable from each other? Because in the middle, the point in the middle is 1 bit of entropy greater than the average of the two, right? Which
Yeah.
means if I am here, which means I don't know if I have up or down, there is 1 bit that I can get, and that 1 bit is going to tell me, oh yes, you have up and you have down.
They maximize the entropy change when being mixed, right?
Yes,
Okay.
right. So in quantum mechanics, the elements of the sphere are going to have 0 entropy. The middle point is going to have 1 bit of entropy, and everything as you go inside the sphere, you get more and more entropy. And so to have 2 points that have the middle points that increase things that increases the entropy by 1 bit, they have to be at the antipodes. They have to be opposite of each other. The line that connects them has to go through the middle point. Now, it is not clear to me whether, like, how to generalize this. Can you have a measurement that sort of that is between 2 things, right? But of course, you're not gonna be able to have 100%. That should be a POVM, like the generalization of a projective measurement is what is it? positive operator value measurement. Is that the acronym? So it's a generalization
Objective operator valued measure.
where you measure, right? So that's a different way in quantum mechanics to define to define measurement. Is what you use in quantum information theory. It would be interesting to know whether there is a sort of a way to generalize that again in an abstract ensemble space where we just know that we have convexity, where we know that we have an ensemble, and you say, okay, this is the best that we can do in those cases, and then lo and behold, in quantum mechanics, they become POVMs, right? I do not have yet at all. So right now, let's just imagine that we have a projective measurement, which means the output of the measurement are going to be a zero, right? Is they're going to be either a spin up or a spin down, right? So if the outcome was a spin up 100% of the time, again, it's not a single take, right? Because a single take tells you nothing. This is another problem in quantum mechanics, that measurements are always thought as a single thing. I have a particle coming in and I do a measurement and I either measure spin up and spin down. That does not tell you anything about the state that was coming in. If you do it once, right, unless you have the perfect preparation of spin up, of spin down, and things are perfectly aligned, you basically get no information. And even in the case where things are perfectly aligned, the only thing that you're able to know that if you measure spin up, then the particle coming in was not spin down. Because even if it was like spin down, but like, 50% off of spin down, like you would have a chance of measuring spin up. And so a single measurement, like a single take measure tells you nothing. So what you need to have is again an ensemble, a procedure that is repeatable, that it's always prepared the same ensemble. You have to repeat the measurement over and over, gather statistics, and then from the statistics, you're going to be able to say something, right? So what's going to happen like geometrically is, again, let's get our block ball. Let's say I'm measuring spin up and spin down, right? The only thing that I'm going to be able to measurement, let's say up and down, is a statistical mixture between these two things. So the only thing that I can tell is whether I am on which point of the axis I am. Because the only thing that I'm going to be able to measure is going to be a classical statistical mixture of spin up and spin down. That's it. So if I'm at another point, what's going to happen is that I'm going to have to find the closest statistical mixture to that, which is going to be this point. And then the measurement device is going to measure this ensemble here. Okay? Now, in terms of preparation, this thing could be a mixture of these two. This thing could be a mixture of these two, right? So this same ensemble that I start with, it could have been prepared by having a mixture of these two procedure or a mixture of these two procedure, right? There are many ways that you can create the mixture, right? But then when I take the data out, this has to be projected on this subset, right? So that forms a classical context. And then I measure the probability distribution.
Oh, yeah, that makes sense.
Okay?
Yeah.
So this is precise, right? This you understand what the model in physically is. We always have these ensembles. We measure ensembles, and so what I still don't know how to do, but I think there should be a way to do it. You see the map between this and this, right? It's a map inside the ensemble space. Right? I start with this and I get something else. You could think it as a map within the same ensemble space, or you could think it as a map between the ensemble space of the quantum state out to an ensemble space of a classical measurement.
Yeah.
Right? And how can I say? And the map has to be, in some sense, not really invertible, but you need to be able to know, well, if I measured this particular classical ensemble, which are the possible states that are compatible with that statistical measurement. And so in any case, you need to be able to say, okay, if I measured, this point here, I could have been on this disk because any of those points of this disk are compatible with that measurement. And clearly, any point, like any preparation, is going to have to give me some statistical distribution, right? And so you need to be able to sort of see the whole space as a foliation, right, of things that come from that statistical measurement. And lo and behold, so if I imagine that I have, I have the ensemble space of the quantum states, I can think in first to project it on something that is exactly a classical space and then map out. And it's going to be the same than mapping out directly. I can map everything to a point that sort of is representative for that classical context and then map out. And I think this is the projection. So the thing that takes this disk and maps it to that single point is what we call the projection. But now it's a projection on the space of ensemble. And so it's just going to be a projection operator like you have in our N, except that, of course, we need to be able to do it in infinite dimension.
Yeah. So you project on a specific basis defined by the measurement, and then
Exactly.
it's, yeah.
So these are basically just can I say, a re-expression of the same thing that we standardly do in quantum mechanics, just putting in the same context of ensemble spaces because we want to have a single mathematical structure from which we can go and get all the pieces. Like we don't want to have this weird thing where in classical mechanics you use these points and this probability distribution. Then in quantum mechanics you use this Hilbert space and these density operators, and it's completely different. Like we want to have something that works exactly the same in both cases, right? Because if you already have a classical space, the thing is the same. It's just that this projection is a trivial operation because they're already projected. There's nothing to do.
Okay. What I'm now lacking is the connection to the whole Choquet theory business. Like, what's the measure? You somehow want to replace. You want to have a measure defined on the extreme points, and then think about all the points as measures or something like this.
Yeah.
You know what? So
okay. So let's talk about
how does it
Choquet
work?
theory. Okay, so let's suppose that we have, let's do the simple thing first. Let's start with a nice and classical triangle. There you go. I have a triangle, right? Now, what happens for a triangle? A triangle is a convex space. Convex, meaning that if you have take 2 points, then any linear combination where the coefficients are from 0 to 1 ends inside. So if you take 2 points, any point in between is inside the convex space. So this is not a convex space because if you take this and this, you go in the middle and there is nothing there. So that's not a convex space. But this is a convex space. In a convex
This is our
space,
ensemble space.
what?
This is our ensemble space.
This is going to be an ensemble space, yes.
Yeah. Okay.
Okay. But right now, let's just think it just mathematically for now. It's just a convex set, a convex set, meaning that it's a subset of a real vector space that is convex, meaning that if you take 2 points and make a sort of the line between them, right, the segment between them is fully contained inside the space. For every convex set, you can define the set of extreme points. And in this case, it would be these 3 points. And the extreme points are the points that cannot be expressed as a convex combination, right? So if I have this point in the middle, I can say, well, this is a convex combination of those two, because I have 2 points and that point is in the middle. Even here, if I take these 2 points, well, these 2 points is in the middle of these two vertices. So those are not extreme points. But the vertices cannot be decomposed like that. So those are called the extreme points of the convex set. And if the convex set is closed and compact, then you are guaranteed that the convex set is the hull of the extreme point, so that any point in the middle, right, is a convex combination of the extreme points. So how do I get this point, for example? I could get it first by mixing these two, and get this one, and then mixing this one with this, and there you go, I get this point. Okay, so any point in a convex set in finite dimension, if I have something closed and convex, it's very easy to show that every point can be expressed as a convex combination. So if I have a point E, this is going to be a sum of the elements of the extreme points. I guess let's call it A, and let's call the extreme points E, right? So it's going to be a PI over EI, where PI is in 0 and 1, and the PI sum to 1. Okay?
Yeah. Is there an obvious connection to the other bases that we have, like for, I don't know, sigma algebra, topology, something?
So this is a simplex. And a simplex is something where essentially, how can I define this? Well, the simplex is just this process where you take a point, and then you take 2 points and you have a line. And now you take essentially 3 points and you have a triangle, and you have 4 points and you have a well, I always forget the name of this, a tetrahedron, right? And you can see that every time the face of this is a one of the lower dimension, right? So now the face
Yeah.
here becomes this, and the face here becomes this, right? And these are simplexes, and the simplex is a representation of a finite probability space. So if I have a sample space that is made by, let's call them EI, because why not, or by n points, right? And then what's going to happen is that the set of probability distribution, PIs, right, is represented by a simplex.
By points in the simplex. Yeah.
Right. So every point in the simplex is a particular probability distribution.
Yeah.
Okay? Now, what Choquet theory wants to do is generalize this to the case where you do not have finitely many points.
Okay.
Right? Or you do not have a simplex. So
Okay.
in the case of when I don't have a simplex, so let's say that I have a circle. A circle is a convex set. And I can still say that any point inside the circle, any point in the circle, can be expressed as a convex combination of extreme points. Now, the extreme points are going to be the elements on the circumference. These are all extreme points. Because if you take one, right, and if you take the line, sort of a line here, it's either you're always out or you're half in and half out. So this point will never be able to be expressed as a convex combination of 2 points.
Yeah,
So,
that makes sense.
okay, so all the points on the circumference are extreme points. If I have a point here, now I can say, well, if I take a line that connects the two, this element is a convex combination of this and this.
Yep.
But it's also a convex combination of this and this. And it's also a convex combination of this and this, and so on. So I can represent this point as a convex combination of elements of extreme points, but that representation is not unique.
Okay.
If you want it to be unique, you need a simplest.
Always? By
Yes.
definition? Okay.
Yeah. Right? And so Choquet theory wants to make this statement on an infinite on a set of infinite points. You want to say now these are always we visualize them in our n, right? These are subsets over n. Now I want to have something that it's a subset of R infinity, which of course doesn't make any sense. So you say this is a locally convex topological vector space. And now you're going to have, and let's call this E. E is my local, and we don't talk about this because that's ill-defined. So you say I have a locally convex topological vector space. What is that? It's something that has an addition that can take two elements of E and gives you an element of E. And this is continuous. And then you have your scalar multiplication that takes a real number and a E, and it gives you another E, and this is also continuous in the topology. And this is what a topological vector space is the vector space where the sum and the scalar multiplication are continuous. There's nothing else. The fact that it's locally convex, that is a little bit more difficult to explain. And one way to look at it, if I remember correctly, is that you have, what is it, a neighborhood system made of convex sets, I think. So basically, if you take, let's say, the origin, and you take all the neighborhoods of the origin, which means all the sets that contain the origin, and you take a set, the open neighborhood that are convex, that would form a basis for all the neighborhoods, for the open neighborhoods, I think, of the origin. And once you have that for the origin, you have it because the topology is translation invariant, you have it everywhere else. Should be kind of something like that. I don't recall. Go ahead. You were saying something?
So yeah, that kind of makes sense. So
it should be something like that.
Yeah.
There is a different characterization that is a lot more important to me in terms of semi-norms, meaning that the topology can be generated by a countable set of semi-norms, and I think that those countable set of semi-norms can be associated with experimental quantities that we go out and measure. So I think that that's a better characterization for us physically, like it would make more sense. But whatever. It's for now, it's a definition. Let's just take it as a definition. Then the idea is, so this is basically the generalization of Rn to the infinite case. And then you're still going to be able to say, I have a compact set that is the hull of, let's say, let's call it a hull of another compact set C. And then what you are going to be able to show is that every element of K, right, it can be seen as a convex combination, which basically becomes a probability measure on the continuum or on a generic set. Every element of K can be seen as a probability measure on the extreme points. So these are the extreme points.
The extreme points would actually be like a sample space.
The extreme points would be the sample space, yeah. So
Yeah.
we could actually call these essentially omega because they are basically omega.
Okay.
And I am still trying to figure out the details exactly what they are and how they work. But yeah, that's sort of the idea of Choquet theory. And for us, how does that connect from us? Because we have our axioms that tells us that any ensemble space E, let's write it script E, ensemble space is a subset, actually a bounded subset of a vector space. Okay, so we know this in general because we are able to prove it in general. What we do not know is that the topology of E is the same as the topology of a locally convex vector space. That we do not know in general. We do not know how to get it. But we should be able to say that if E is, let's say, quantifiable, I think I call it, or something like that. The names are always things that we'll figure out once we have everything going. If there are a set, a countable Fs that take E and brings it to R, such that these are affine, meaning that F of PA plus P bar B, and P bar is just 1 minus P, is equal to PF of A plus P bar of B, meaning that the quantity over a mixture is the average of the quantity, meaning that this is a statistical quantity.
So the same as
But
the random variable.
yes, it would be the
Yeah.
random variable.
Yeah. Okay.
It should be a random variable for a classical probability, and it will be an observable in quantum mechanics. They both have this property.
Yeah. Okay.
And if we have something where you have this countable set, what I think can be done, I have the sketch of the proof. I think I even have the proof. I have to go back and look at it to make sure that everything works in the way that it should work. Then under this assumption, epsilon it basically is a bounded subset of a locally convex topological vector space. Now we have bounded, we do not have compact.
Yeah.
And I'm pretty sure that when we're going to have, since we want this thing to work at some point for field theory as well, it cannot be compact because any topological vector space that is compact or locally compact is finite dimensional. And we will need to work with the space of field configurations, which has to be infinite dimensional. And I'm pretty sure that we are going to need to put the distribution on those things. And that's Yeah, so we're not going to have a compact thing, and so the whole problem there is to understand how to tame that infinity with tools that are not the standard tools that people use, because the standard tools that people use are not going to work in that case.
Yeah, okay.
So, okay, so does that cover?
So we want still, what exactly is the measure that we want? So
Okay, so how do we get to measure? So you understand that I want to have a point, and the point is the sum of pi of the extreme points, right?
yeah, there's not just one way to do that.
Yeah. But
Yeah.
there exists at least one way, and this one way is going to be a sequence of P1, P2, and so on that sum to one.
Yeah, so the measure would be just a probability measure of like probabilities assigned to the way this state was prepared.
Right.
But I could choose like different states, like a different basis in quantum mechanics.
Yeah.
Okay. Yeah.
Okay.
Okay.
So basically, what you should think of this convex combination, you shouldn't really be thinking as probability again. You should think it as mixture, because the same state can be prepared by using different mixtures of different starting points. But the point is that here I'm writing it in the discrete case, right? These are probability, and these are elements of the sample space, right? I'm just doing like simple convex combination of points. I don't have a measure here.
Yeah.
So what needs to happen is we need to take this and make it become something like this. Right, let's see how I can write it in a way that it would kind of make sense. Okay, let's just write it like this for now. And let's say E, and then over the whole, there you go. Like this is kind of what we would like to write.
The dp would depend on E, and that would be the measure, right?
Right.
Okay.
So now P is something that it's a measure, so you give it a set, and it gives you a number from 0 to 1. Right? And yeah, and that's it. And A is a subset of the sample space.
Yeah.
Okay. Now, of course, we're not going to write this because this makes no sense.
Okay.
Okay. So what does it mean that we can associate this X to this P? Okay. It's going to mean the following. It's going to mean that for every let's say that let's see, how do we call it? Okay, so let's say that we have the sample space. This is our sample space. These are the extreme points. And then we have our ensemble space E, right? And this we would want to represent with the set of measures of probability measures on omega, right? This is we want to make this identification. For every point here,
Okay.
we have a point here, and we can go back and forth.
Yes.
Okay, so how do we do it? We are going to have a set of continuous functions over the extreme points. So every element here is an f that takes an element of the extreme points and gives us a number.
Yeah.
And then we also want to have an f, like a set of let's say linear functions or on a fine function on on our ensemble space. So we have a big F that takes an element of the ensemble space that gives us an R, and this is affine.
Yeah.
Okay? And so we want to say that for any E in big E, there exists a mu in M1 sample space such that f of E is equal to the integral of f of, let's say, x d mu over the sample space.
So each element in my ensemble is something that allows me to evaluate, I guess, something like averages of observables or something like this.
Yeah.
Okay. Yeah.
Okay, so what I really have from our perspective are these objects, right? We have the statistical thing because those are the things that we measure, and we have the ensembles that those are the things that we measure. And then we're going to have a set of extreme points, and then those in our mind are going to be the limits because some of these are not going to be properly ensembled, like something like a delta Dirac, a Dirac measure. It's not something that we can have a preparation procedure that always prepares the particle at exactly pi, right? We're never going to be able to do that, right? But we can think of our ensemble as something that is a smeared out version, a probability distribution over these idealized, perfectly prepared points.
Okay. But I guess the problem is not to find any kind of measure. The
Mhm.
problem is that we have like more than one option. Does that make sense?
Yeah, you can have more than one option. It's that itself is not a problem. In quantum mechanics, that's exactly what you're going to
Yeah,
have.
yeah. Okay. So it's the problem that we cannot show yet. Like we want to prove that there exists a mu always, so that we can replace the elements of our ensemble with the mu. So this is like in Choquet theory, I guess they prove that this always exists, right?
Provided that you have a convex subset of a locally convex,
Okay.
sorry, compact subset of a locally convex topological vector space.
And we basically want to show the same or something slightly different in our context.
You're right. So
Okay.
ideally, we would like to show that you do not need. So first of all, like the first problem that we're going to have is that even for something like where the sample space are the number from the real number from 0 to 1, right? The set of measure that our set of measures is not going to be compact because we are not going to be able to include the direct measures, right? So we need a procedure that basically says this is the set of measure that we have that we are interesting. How do we get to those extreme points? How do we get the points of the sample space in the case where the points of the sample space are not strictly ensembles themselves?
So now it feels like you're going in another direction. You know what the measures are, and you want to
I,
find out.
I know what the ensembles are. I do not know the measures. You see, I have E, and so I
Yeah,
know that there are some linear functionals on E, that I know. And I
yeah.
know that there is a convex structure that I can take elements of E and mix them together.
Yeah.
I do not know that those can be represented by measures.
Okay.
What I need to show is that hopefully in the general case, I have a standard procedure to take E and and all these linear functional, right? And define some some limits of these things that are going to go outside of E, right? And those are going to be the space of my points that are not going to be technically ensembles because they are too refined to be ensembles. And then we can show still that any element of E can be seen as a measure on those set of idealized points.
We start with the ensemble space. We don't have the sample space yet.
Correct.
So first we somehow get the limit points to find the sample space.
Right.
And on that, we now can define measures. And these should then represent again the elements of my ensemble space.
Yes.
Okay, yeah.
And it will depend on which of these linear functional do we have and the relationship between the linear functional. That's the thing that should tell you what the space of extreme points will look like, right? So
Yeah.
ideally, we should have a general construction that always works. But then when you know more, oh, but in this case you have this type of statistical variable, and they look like this. Oh, then it means you're in a classical space, or it means that you are, in a field theory case or whatever.
Okay.
So that's the goal. Whether we're gonna do it and how much new math needs to be developed for this and so on, I have no idea.
Yeah.
But it mimics the sort of the way that we should construct the way we construct things or model things when we're doing the experimental work. Because again, what we do before we can do anything and so on, well, we need to create one preparation devices to be able to prepare a sample in consistent ways. Okay, we need to have a set of ensembles, and then you have your measurement apparatus that has to be reliable. And so you need to calibrate, you need to all that. And what does calibration mean? Well, it means preparing particular ensembles that you know how they're composed. And then you look at the output, the ensemble that is the output of the measurement device, and you can say, aha, this is correct because this is exactly what I've put in. So you know how now all the things that you have mapped in your space, and then you take something that you don't know what it is, and then you can make these maps, right? And and again, your measurement apparatus never measure points, so it always measures things that are in intervals. You gather statistics, you make your histograms. Those are the things that you do. And the points, right? We idealize things with real numbers because we have in our mind that our measurement apparatus can always be made more and more and more precise, so that our uncertainties shrink, shrink, and shrink. And so we have all these possible statements that we can go and verify experimentally and blah, 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 right? So
Yeah.
that's what we need to try and reproduce.
Okay, so the step from like taking the limit points, that is not really what Choquet theory is about. That's just the second step, right? Once I know the sample space, if I satisfy all the requirements, I guess they will tell me I can use measures, maybe
Yeah,
not uniquely, to represent the points of my ensemble.
yeah.
So, where are we in like determining, like figuring out how to take these limit points? You said it should work like this, like somehow you had an idea, but there
So I
is
had many ideas that failed, and
okay.
then so the original idea that failed were not taking advantage of the function themselves, so like the outcome of the quantities that you can go and measure. What I
Yeah,
was trying to do it was just purely on the structure of the convex sets and the structure of subspaces defined by the convex sets and by the entropy. And what I realized 3 weeks ago was that that was never going to work. So I do not have a current strategy of how to do it. what the plan would be is to understand when and how Choquet theory works, and then understand whether the techniques that they use can be recycled in a more general case with the other things that we have, and
Mm.
then whether there exists a notion of compact closure or something like that that we need that we might use. So basically, what we need to understand, even in the simple case, is how we go from the space of um, essentially a continuous, absolutely continuous probability measures over the reals, right? And these are not gonna include the delta directs, the direct measures, because the direct measure is not a function, it's not absolutely continuous. It gives you probability one on a set of measures zero, so it's not absolutely continuous. But there is still a sense that these are limits of uh, absolutely continuous measures, because you take a finite interval, right? And you shrink the finite interval to zero. Well, and with a uniform distribution, you shrink it to zero, you're going to get a direct measure. So there is a sense where the direct measure is a limit of that, but also not all the limits are going to be measured that we're interested in. Because if I have a measure where, for example, we'll need measures defined over the whole real, right? If I take a measure that is uniform in a finite subset and I make it, I shift it to infinity, that is again the limit of a set of measures that we're interested in, but the limit is not, right? There is something that goes to infinity. So it needs to be clear how that part works. How do we get these limits for the points? I still do not know. I have a couple of ideas, but I have no idea whether they're going to work out.
And these functions f, like my statistical quantities, they somehow have to define which ones converge and which ones don't.
Right.
Okay. Yeah.
So the thing that occurred me this morning was that I don't know if we would have time. Like we already 12:30, so maybe we can discuss it another time. But the point is that if I have a measure that is absolutely continuous, I think that knowing all the moments of the distribution is enough to recover the measure. So if I know the expectation of x, the expectation of x squared, the expectation of x to the third, right, all the finite powers, I should be able to recover the probability distribution on the assumption that the measure is absolutely continuous. Because that would mean I have a continuous function, and it needs to be Schwartz because it needs to go down at infinity faster than any polynomial, and the Schwartz space is a Frechet space. I have countably many semi measures which are going to be the moments, and I'm going to be able to fully identify a point. So I should be able to, if I know all the moments, I am able to get to the value, to the distribution.
If I would think in terms of functions, that's literally like a Taylor expansion, right? If I know all the coefficients for all the powers, I would know the function, right?
It's
It's
a different
distribution form.
expansion.
What? Sorry?
It should be a different expansion because what you know are the averages, right? You know the integral of x to the n times f. That's what you know.
Mhm.
It's not a Taylor expansion. So let's say
Yeah.
the variance tells you something global about the function, not something local about this function.
Yeah, I was just thinking if I consider my distribution to be something like a linear functional, and then I can feed it any polynomial. Then if I had like a one-to-one correspondence between functions and distributions, then I basically um, can think of it as a Taylor expansion. I don't know. You probably wouldn't pick out the coefficient in front of x squared if you measure the variance. Okay, maybe this is something else, but
So I studied these things as part of probability theory and statistics, like what was it? Probably 30 years ago or something like that, 20 years ago. And there is so the problem of reconstructing the distribution from the moment is called the hamburger problem,
Mhm.
and don't think it has anything to do with the sandwich, but the guy I think was called hamburger, and there are theorems on all this stuff, and if I remember correctly, they use the moment generating function. And there is a Taylor expansion of the moment generating function that might relate to the moments. And so there might be a sense in what, some of the things that you're saying are going to make sense in that sense, but it's a very precise sense and you have to go and look at it,
Okay.
which I don't know it off the top of my head.
Okay, where did we stop? We wanted to find out whether the Fs are enough to define the probability measure, right?
Right. So I think we are going to be guaranteed, like in the case here that we say that we have an ensemble space that is quantifiable, we are assuming that we have enough Fs.
Yes, and specifically, you expected that all the powers of position
Yeah.
are enough to get all the absolutely continuous probability measures
Right.
on the real line. Okay.
Now, the thing that is interesting is that there is something else that people have been doing in quantum logic and other things, which is called the GNS constructions. I don't know if you have ever heard of it. It's a way
Maybe.
that you start with a C-star algebra of observable, and then you define states as linear map from the C-star algebra to R, and then you show that these are elements of a Hilbert space.
This specifically for quantum mechanics?
It's specifically for quantum mechanics.
Okay.
My hunch is that we basically want to have a Choquet-like theory. So we want to basically take all these things and merge them all together. The requirements of the C-star algebra is that you're going to be able to make products. And I do not understand, right? Because if we start with just saying, oh, I have, this thing, I have affine functions, right? And I have two of them. How do I know that one is the product, the square of the other? Like that part to me, it's completely unknown. Like I don't, I do not know, I do not know how it works. It could be, okay, it could be that we need more structure to be able to get all this done. It could be that we need already the Poisson structure on observables to then basically have a notion that we have a symplectic space and blah, 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 all these things. But I do not know yet. But it's something that I have in the back of my head because, again, I tried doing this without knowing about the observables, and I can prove that it's not possible. So the next step is say, okay, let's assume that we have observable and we have enough observables to identify things. Is this enough to be able to define the points? For example, can I just think of the points as the countable sequence of all the outputs of the observables, right? Because those are going to be able to identify specifically an ensemble, right? And so can I think of the limit points as the limit points in that space, right? But then how do I know which one are the correct elements? Because if I have the space of Schwartz distributions, right? And then I basically know that the averages of polynomial of position and momentum or just let's just say the moments of X. Let's just stay single variables for now, right? Okay, so we know that those are all going to converge and so on. Those are not all the affine linear functions. The the value of the distribution of a point, right, is a linear function, right? If you take a set of probability distribution and you present them as continuous function, then you take the density at a single point. That operation that takes the density of a single point is a linear function, right?
Yeah.
It's how people define the delta Dirac as a distribution, as a function that acts on the space of Schwartz functions, right?
Yeah.
But that observable, that thing, right? It's exactly the thing that goes to infinity when you take the limit and you need to find the points. So the thing that is confusing to me, and I still don't know how to do it, and this is why it's research, how do I know which are the countable set of values that are good, that are going to remain finite when I make the limit, and which one that are not? I have no idea. And I think on that note, I'm starting to be too tired, and it's after 12:40, so I don't know that I can make coherent sense anymore.
Okay. So you don't know which sequences of measures will explode when I
Of, uh,
take
of,
expectation.
of statistical quantities.
Yeah, yeah. Okay. So our selection of the statistical quantities somehow, and this is the non-obvious part, restricts which measures still give us like physical answers, like finite expectation values.
Right. So we want all the expectation values to be finite, right? So we are going to have a set of quantities that are special, that are always finite, that are enough to fully identify the ensembles that we will always need. But then there are going to be others.
Okay.
Okay.
Yeah, I think that was very helpful, at least to me.
Good. I hope
Thank
that
you.
it was interesting to somebody else as well. If it was interesting to you, please let me know because sometimes it's hard to just talk to nobody. At least I have Tobias. I wouldn't be able to do it without you, Tobias, this I have to say. Okay, so we'll close it
Yeah.
and we'll see and talk next week. Bye.
Okay. Bye.